The next speaker is Florent Monjalet, who has been working at CA for more than 4 years, first as a security researcher, and then as a system developer in the HPC storage team.
Thank you, Thomas. Hi, everyone. So I'm going to present you a research that we conducted to build smarter policies for data movement by predicting the file lifetimes with machine learning techniques. Does it work? Yes, great. So actually, Lix's talk is a perfect and much more extensive introduction that I did here, so I will be quite quick on this. But as you all know now, at least, we tend to have top tiers that are very fast, but lower in capacity than bottom tiers that have much larger capacity for the same cost, but have way lower performances, especially if you think about tapes. And the data movements between these tiers can be very expensive in themselves. So what we usually do is that we use our top tiers for the files that we use regularly, and then we move these files out of the top tiers to the bottom tiers when we don't use them anymore. The sooner we are able to move these files out of the top tier, the more capacity we can have for the same cost on the top tier. However, if we move them too soon, the problem is that we are going to pay the performance cost of retrieving the data in the bottom tier. So that's the context. So as Jim mentions, there are multiple ways of selecting which files to move to bottom tiers. One is LRU policy. One other is to say, okay, every file that haven't been accessed for 1 month gets out of the top tier. We can go in further details, maybe by specifying patterns for paths, saying, I know that log files of these users, well, they are produced for an amount of days, but then they are read for a maximum a week, and then they are not useful anymore. Or, for example, most checkpoints are written but never read again. Most of them, not all of them, of course. So it's quite tedious work, but quite necessary as well. And it's very tied to user habit if you want to do something that is very tailored and efficient. The approach we took here was to try to infer the file lifetimes by looking at the data that we have. What I'm calling here file lifetime is, for example, the time between the creation of the file and the last time it will be read in its entire lifespan. In our file systems, actually, you have millions or billions of files laying around with this information, and HPC users tend to be very regular in their namings, etc. So it's actually interesting to see if we can predict for how much time a file will be used. For this, we used. I'm presenting two approaches. One that is more cost-effective in terms of computation, which is random forests. Another one which is a bit heavier, to say the least, which is convolutional neural networks. I'm going to go a bit more into details on this algorithm a bit later. The two main advantages of this approach is that estimating accurately the lifetime of files can give another very interesting input to build efficient and smart data movement policies, which can be, of course, mixed with the things that we know how to do today. But this is more information to make more educated guesses. The other thing that is very nice is that machine learning algorithms learn on the data without any human interactions, so that if you train your algorithm regularly, it will just follow user behaviors without you having to track this behavior manually, which is very interesting. So I'm going to present first how we specify the problem. We're going to take a look at the data sets, And then I will present both algorithm I used, and then in the next part we will have results. So the more suspense, the more enjoyment. Okay, so first, if we are going to use machine learning, we have to write precisely the problem that we are going to solve, which here seems very simple and simplistic. We have just file path, no other information. That's the first step. So for a path, we want to output a number, which is the duration, so the probable duration of life for this file. Just 20 seconds, 30 days, something like that. As I said, in this presentation, I mostly present results for lifetimes that are from creation to last read. But actually, the whole method is totally independent of this definition. It works with whatever number you give it that is correlated to the file path. So you can use other definition and use the same algorithms. Another important point is that rather than only estimating very accurately the lifetimes of the files, we really don't want to underestimate them. Because if we underestimate the lifetime of a file, we take the risk of moving it too soon to a bottom tier and then paying the performance cost to retrieve it later, and this we really don't want. So we want a decent accuracy, but very importantly, we don't want to underestimate this lifetime for these results to be actually useful in real life. Our dataset was constituted of about 6 million files, where we had the absolute path, creation, last access time, and last modification time. We extracted this from Robinhood database of a production file system that we have, which has the interest of hosting very diverse populations of users, so it makes it an interesting data set. For the dataset, so as you can see on this graph, it's density, so don't really bother about the numbers here. Just this number is very important. This is long-term storage, and we can see that actually half of the files are never accessed after they are created. And when you look a bit further into it, it actually represents about half of the capacity of this tier that is used for files that will never be read again. So that's an interesting thing to see. But another thing that it implies is that when we are going to predict the lifetimes, we have to be very wary that our algorithm just doesn't just say that, well, all files will live 10 seconds and then it gives me a good accuracy. We have to make sure that its performance is good over the whole range of durations that we see in the wild. So, now we know a bit more about our problem. We saw our data sets, and now we have to feed this data set into our algorithms. Here starts the real work. So the algorithms I'm working with, and lots of machine learning algorithms work on fixed size vectors of numbers. However, paths are not fixed size, and they are not numbers. So we have to do a bit of work to transform them into fixed size vectors of numbers. We have to do this in a way that expresses the statistical nature of what a path is. I'm going to go a bit more further on this later, because if we don't, we take the risk of inducing biases in the network and not having ideal results. So the way we transform these paths into vectors, the first, I think everyone could have found this on their own. We just truncate or left pad the paths so that they are fixed size. So this is the easy work. So we have a path here, we left pad it, and if it's too long, well, we truncate it. And 256 is actually a good value so that you don't truncate too much paths in your data sets. and so that you retain maximum information without having gigantic vectors as input for your algorithm. The next step is to transform each letter into a number or into a vector of number. The naive approach would be to say, okay, these are ASCII characters, so A is 65, B is 66, etc. The problem with doing that is that what you are telling the network is that A and B are very similar, but A and Z are quite different, where in real life, A and B and A and Z are probably as similar. So the encoding we use is a classic encoding that we use in machine learning, which is called one-hot encoding, which consists in transforming each letter into a vector of which value is 0 everywhere, but in one index that corresponds to this letter. So, for example, you see 0 is 1 at index 0 and 0 elsewhere. Slash is 0 everywhere, but in index 2 it's 1, etc., etc. By using this encoding, each letter is encoded into a vector that is orthogonal to all the others, and everything is equidistant, and we don't introduce any bias to the algorithm. So we started with simple strings, and now we have big matrix, well, relatively big matrix of 256, which is the length of our path, times 106, which is the size of the alphabet in our dataset, so the amount of different letters that we saw in the input alphabets. So we handled the input. Now we have to handle the output too. Durations have a high dynamic range, and when you think about it instinctively, errors on duration are more multiplicative than additive. For example, if you make an error of 1,000 seconds for a duration of 1 billion seconds, well, you don't really care. But if you make an error of 1,000 seconds on a duration that is only 10 seconds, well, it makes a big difference. So what you really want to express are differences that are multiplicative, because if you multiply any of this duration by 10, well, instinctively it represents how we perceive the error on times. What you're really interested in is the order of magnitude of duration. So that's why we are logarithm scaling the durations. So for the first algorithm I'll be working with, to be honest, I tried a bunch of algorithms that are in scikit-learn. I knew this one was a good candidate, and actually that was the one that worked the best. The idea is that you train a number of decision trees. Here 16 decision trees. Each decision tree doesn't see the whole input, but a random subset of it. And then you combine all these decision trees to make a guess on the final prediction you want to make. This is quite computationally effective and a light method that gives nice results, as we will see later. Next, this is, as I said, a heavier method, but a finer one. I tried convolutional neural networks, which have been known to be very efficient at working with patterns of things, namely in image recognition. Paths can actually be seen as sequences of patterns, so convolutional neural networks make good candidates to be tried on this problem. The architecture can sometimes look like black magic to people that don't do machine learning. The one I used is mainly inspired from the literature on the subject, but just to give you a rough understanding of the different layers that exist. The first layer is called an embedding, which is meant to reduce the dimension of the inputs so that the letters that can be easily swappable. For example, in a path, A and B may be easily swappable, but not A and slash. So after these layers, each letter will have a value in a space of dimension 32 here, that will be very close to the other letters that it can be swapped with, but very far from letters that it cannot be swapped with. Instinctively, it allows the network to be resilient to insignificant changes in the input. The next layers in green are the so-called convolution layers. What they do is that they learn relevant patterns in the inputs. So that's called feature extraction. So after these layers, we will have a set of abstract features that correspond to patterns in the inputs. And the last layers are just there to do the big computation of what is the lifetime associated with the features that we learned with the convolution layers. That's the Roth instinctive understanding of these black magic architectures. Another important point in neural network is the loss function. The loss function is the function that we want to optimize so that the network becomes good at predicting what we want it to predict. And it will really determine how the network weight will be updated. I experimented with several losses. I'm presenting two here. The first is log cosh, which is a loss that gives a very, very good accuracy, but is quite resilient to outliers. So if you have very improbable values in your data sets, they will not make your network diverge. This loss will allow to be quite resilient to these strange values. The other is a bit more exotic. It's called quantile 99. What this loss is a loss that really penalizes underestimation much more than overestimation, which results in a lesser accuracy, but with a very low rate of underestimation, which is theoretically about 1%, because we aim for actually the 99th quantile of the statistical repartition. The important thing is this will give an overestimating network rather than an underestimating network, which is, if you remember well, really what we want in the end. So for the results, I'm going to demonstrate two training situations. In the first, I'm training on 70% of the training sets. And then I'm going to validate on 30%, which means that all the results that you will see here are the results, the accuracy of the prediction on data that has never been seen before by the network, which are 30% of the data set. The other training situation is by training on 95%, so most of the sets, and then just validating on 5%. The interest of doing both these approaches is to see if feeding the network with more values allows it to be better performing, or if it already learns all that it could on less data. For the training times, as I mentioned before, random forest is much cheaper, because it's a 5-minute training on 24 CPUs, whereas for the neural network, for these results, I trained 2 to 3 hours on 4 very high-end GPUs, which is a lot more computation than 5 minutes on 24 CPUs. Also, for all these results, the error I will be showing will be the ratio truth divided by prediction. For the random forest regressor, there are lots of numbers. Actually, only 2 matters. I should have put them in bold, but the 96 something percent is the amount of prediction that are within a factor 10 away from the truth. So these are actually pretty usable to make good guesses on what to do with the data. So 96% of the time, these estimations are good. That's what I'm going to call accuracy later on. The other important thing I mentioned was the underestimation rate, which we want to be very low. Actually, if we look at the data, only about 2% of the estimations are more than a factor 10 away from the truth and under the truth. So these are actually the estimations that are going to cause trouble because these are bad estimations. And here they represent about 2% of the prediction we do. The two graphs that are underneath, the first roughly shows that for all the durations, on the whole duration value range, the accuracy is relatively consistent, meaning that it will be as good to predict long duration than short duration. This is the error repartition of the prediction, which is well centered around error 0 and quite narrow. If we push this algorithm by learning on 95% of the data, we see that actually there's not much improvements, which can either mean that the algorithm is not expressive enough, or that it just learns all the variance it could learn on the data set. Actually, on this data set, I believe that it means that the data set is very regular and there is not much more to learn in 95% of the data set than there is to learn on 70%. Next, for the convolutional neural networks, there are two results for the two losses I mentioned before. The important numbers here again are that with log-cosh we are nearing 99% of the prediction that are within a factor 10 away from the truth. So that's becoming to be very, very accurate. With only 0.6 that are unusable. And for the quantile 99, we see that we have an accuracy that is not as good, but still decent, about 95%. However, only 0.1% of the prediction can lead to bad decision, which means that 99.9% of the time, if you use the results of the quantile 99 predictor, you will make a rather good decision. Here again, the accuracy across the whole range is represented. For log-cosh, it's pretty consistent. For quantile, it drops a bit because it's globally less accurate and it tends to overestimate. So you would expect to have a lower accuracy for small values. And when you look at the error profile, you see in orange the log-cosh error, which is well centered around 0 and a bit narrower than one we saw before. And in blue, this is the error profile of the quantile 99, where you can see that there are very, very few errors that are negatives, and most errors are overestimations that we are not too sad about. The results for training on more data are the same. The network doesn't really improve, which means that actually we can have good performances even when we learn on very few. Very few. 2/3 of the data set is already a big chunk, but it's not that big. As a conclusion, so these are just the numbers that I showed you before, summed up on this slide so that you can keep looking at them while I'm talking. What I can say is that this really looks promising. It's not easy to say that these are good enough numbers for production usage, which is, however, what we can say is that even with just taking the path of a file, we can extract very precise information on how it will behave in the future. And what I expect is that if we feed these networks with more information, we may be able to be even more precise. That's one part. And maybe this is actually the maximum that we can do in terms of prediction, because there is always a part of random of users accessing their data 4 months later than usual because they want to go back on something they did before. So these mispredictions are not a problem in real life. This is still an early work, but I believe it can be an interesting thing to look for. Thank you very much.
Do you have questions?
So you define lifetime as the time from create to last access time?
Yes.
So again, and you also gathered stuff from Robinhood databases, but I didn't think Robinhood tracked access times.
Actually, it tracks. I think that's the last read. Actually, I had last access time. You can have last read or last write. I'm not sure. I will have to, double check this. But we have roughly the last file system scan will be accurate enough to, train the network, even if the data is not real time.
Okay, yeah.
Yeah.
I mean, it's the same problem from the last presentation that the changelog just don't have the access time, so it's just hard to. It's fundamentally kind of a limitation. You don't have the data, I think, for that.
You can activate the 8-time changelog. No. If you want to have a meaningful database for that training, you can activate the 8-time changelog. And you can, after you have a fresh scan, you have meaningful 8-time for the training. Do you have other questions?
If we take a little bit distance from those numbers, have you been able to analyze the results and in fact the statistics about those lifetimes and correlate that with a few factors that would explain why we have this file lifetime distribution? Is it mainly due to the applications? For instance, some applications generate files for which users only have a need for a few days or months, or is it more about the users that are dealing with this data? Have you been able to, try to understand why you have this distribution?
I haven't looked very far into this, but just from what I saw, I tried to determine which part of the input was relevant to the network to determine, well, the output. And it really depended on the paths. For some of them, the user was very relevant, plus some pattern inside the file names. And for other file names, I guess that are totally managed by some program, and the user doesn't use it. Doesn't use it. The user part was pretty useless to the network. I don't have precise statistics on this. Just this is all I have to give you. I'm sorry.
The goal is not to do this work. The goal is you don't have to look at specific application patterns, and you have your algorithm that learn every community by itself, and you don't have to look at.
So let's put it this way. I'm pretty skeptical about the real. In order to know if this is really useful to bother with AI and so forth, maybe sometimes it's good to analyze the results and maybe just think, oh, maybe we could have find by ourselves with some basic thoughts that this distribution is quite makes sense, Or if it's, but Uranus says that it's not really something that could be human predictable, so it's fine.
Okay.
Most of the time, what we see is that the pattern of names says a lot about how the file will be accessed. For example, .log, you can guess what how the file will be written, how it will be reused later. So that's the point.
Do we have time for one more?
Yes.
Okay. Maybe this isn't the point, but if you had to decide how little data you could analyze and still have a proper result, what do you think the littlest percentage of your data set you could have used to get somewhat?
I actually didn't go. That's what I did. This kind of test a while ago. I don't know how much it dropped. I would expect it actually to depend on the data set, which means to depend on the sites where you want to train this kind of network. I think I remember that maybe 50% was still okay, and then it drops gently. I don't have a precise number for this.
Okay, no, thank you.
Sorry.
Thank you, Florent. The next speaker is Olaf Weber, who is a master